Today we're going to be talking about a class of problems of particular importance, and then we're going to be going into slope fields, which are pretty uniquely tied to those class of problems. So the problems that we're going to be talking about are called initial value problems. And the whole idea of initial value problems are you're given a differential equation. So let's say you're given some differential equation dy over dx is equal to y times ln x. So we have this differential equation, and our problem is to find the function y. So to find the function y of x when we're given this differential equation, when given diff eq, so that stands for differential equation, and some initial value, so some y of c is equal to some value a. And the reason why you need this initial value is because if you kind of think about finding the integral that, or to find the function that had the derivative that led to this function, you could have multiple. If you had like a function y that satisfies this dfq, you could kind of think of a function y plus some constant c2 that also satisfies this differential equation because of the fact that the derivative of a constant, so dy over dx of any constant c2 is equal to 0. So there's infinitely many functions that can satisfy a differential equation. And so the only way you can find out the particular function that satisfies a differential equation is if you were also given some point on that function. And so if you have those two pieces of information, then you can ideally single out only one or a few functions that satisfy our initial value problem. So again, in an initial value problem, we're going to be given this a differential equation that determines how y changes with respect to x, and you're going to be given an initial value problem, and the goal is to find out the original function y that led to these two things. And so let's just do an example. And in this case, we're given d of y over dt is equal to 0.056y. And our initial value is y of 0 is equal to 100. And we have to find y of x, or y of t in this case. And the first thing we should do is probably analyze the differential equation. And we're given that it is some constant times y itself. And the best way to go about this is kind of think about what functions would lead to this sort of behavior. And the first thing that pops out to me is exponential functions, because let's just say I have a function y is equal to e to the x, then dy over dx is equal to e to the x. And if I were to replace e to the x by y, because they're both equivalent, I would get dy over dx is simply equal to y. And that is very similar to what I have over here, except the fact that I have a constant. And so if I were to continue on this pathway of pattern matching, and I know like the whole idea of like, oh, let's match a pattern to solve a problem does not seem very satisfying, but in these cases of especially solving differential equations, and if you ever take a class on just diffeqs, this is like the best way that this is done, and it's just how it works. So it's not satisfying, but that's the best thing that you have, and so it just comes out with a lot of practice. So back on track. I was saying that we have this constant, And if you're to further analyze on this path over here, let's say I have e to some constant a times x, then dy over dx of that function is simply equal to a times e to the ax. And again, e to the ax is simply y, right? Because in this case, I said y is equal to e to the ax, and then we have this constant over here. And so we would have a times y. And so now we know exactly what form this function takes on. And so we know y is equal to e to the 0.056 times x. However, if we know anything about exponential functions, is that a constant term over here represents or can change what exponential functions we have. Because, y of 0 could have been like 1,000, 4,000, etc., etc. That does not change the fact, or that would not change how our derivative would react as. And so, on that vein, we got to find out what c is equal to solve this initial value problem. So we're given y of 0 is equal to the constant c times e to the 0.056 times 0, which then will simplify to 1. So y of 0 is equal to c, and y of 0 is simply equal to 100. So 100 is equal to c, and then we have solved our initial value problem by finding y of x is equal to 100 times e to the 0.056 times t. So that is the general workflow of an initial value problem. You got to find out what function leads to this derivative. And once you find out the class of functions or the function that would lead to the derivative that we're given, you then use the fact and the information that we have of the initial value, and then you hone in on the exact function that satisfies both these conditions of both the initial value and the differential equation. Over here, we solved for the derivative, or we solved for the function with this derivative by doing basically a guess and check method of and pattern matching. But a way to solve for these functions is by using integrals. And so you can use indefinite integrals, and that's one main application of indefinite integrals to arrive at a function with the corresponding differential equation. And once you have arrived at that, you can then solve for the constant value, because in an indefinite integral you get this is usually the workflow for an indefinite integral, and then this will be our derivative usually. So you would plug in dy over dx over here, and then you'd get some y plus c, and then you'd solve for that c value likewise. So that's a workflow, but in many cases we cannot find analytically the integral of a differential equation. And what do we do when one we cannot find? And so let me reiterate this on a new page. Many times we cannot pattern match like we just did, nor can we analytically find out and evaluate the indefinite integral. And so in these cases, we're really kind of stuck on knowing how our original function y will behave, right? So again, just to reiterate, initial value problem, you're given some dy over dx, and then you're given y at some constant. And the goal is to find out how y behaves so goal is to find out y of x, or at least know how y behaves as a function of x. And so what do we do when we don't have these two options? Now we gotta kind of rely on numerical methods and graphical methods. And so that's where our solution of slope fields come into play. So slope fields, and so let me define what these are. Definition. So slope fields are essentially a plot of short line segments with slopes f of x comma y for all lattice points. And lattice points just means like integer values of x comma y. So lattice points x comma y in the plane. And let me explain what this is through an example. So essentially what we're doing is, let's say we're given dy over dx is equal to 2x. So slope fields is literally us graphing out the slope at each of these lattice points. So if I were to just draw out this graph, 1, 2, 3, 4, -1, -2, -3, -4, 1, 2, 3, -1, -2, -3. So for y equals 0, our slope is, for x equals 0, our slope is 2 times 0, which is equal to 0. And a slope of 0 corresponds to a horizontal line. So whenever x is 0, because one thing that's simple in this problem is our dy over dx only depends on x and doesn't depend on y. So all values, like if I go up and down the y-axis, the slope field plot's not going to change. But okay, again, when x is 0, our slope is 0, so we have a horizontal line. So we would draw out horizontal lines like this to represent 0 slopes. So all the way down this, I would represent 0 slopes. And I guess just to make it all clear, let me change the color because this will get a bit. So these red lines represent my slope field drawings, and I'm drawing out horizontal lines to represent 0 slopes. Now when y is equal to 1, right, or when x is equal to 1, then my slope is 2 times 1, which is equal to 2. And so at x is equal to 2, I'm roughly going to try to draw out a slope or a segment with a slope of 2. So 1, 1, 2. So it's going to look like this, where my slope is 2. And all the way up and down, I have a slope of 2. Now when x becomes 2, then 2 times 2 is equal to 4. So that's my slope. So in that case, I'm just drawing a steeper line, right? Because my slope is even larger. And if you can imagine, as you continue growing your x's, your lines get steeper and steeper because their slope gets larger and larger. And we're tending towards more vertical lines, right? Not perfectly vertical, but more vertical lines as we're getting into larger x's. So that's our slope field on the positive x side. And on our negative x side, 2 times -1 is simply equal to -2. So our slope's -2 on this side over here. So essentially we're drawing something similar, analogous to the positive side, but just having negative slopes. And again, we get steeper and steeper as the magnitude of the negative number increases. And so this is an example of a slope field where we're just kind of plotting out how the slopes look at various x-y combinations on lattice points. And why are slope fields helpful? Well, in general, the slope field kind of helps us well, let's think about what the derivative is, right? The derivative tells us how a function or how y is changing at a point x. So for each of these lattice points, we're seeing how exactly that function will be changing at that particular point, at that instance. Now let's say so that's cool, right? That's fine, that's cool. But how does this help with initial value problems? Let's say we were now also given a point on the graph, right? So we're given y of 1 is equal to 2. So we're given this value. We're given, so the y of 1 equals 2 just means 1 comma 2 exists at a point in this graph. And so if we can roughly kind of trace out, the slope tells us how that function will change with respect to x. And so it tells us how that function is behaving around this point. So it's telling me, oh, okay, around 1, the next few points are going to be like this. And as I trace out the values, I'm like, oh, I'll end up around 2 comma 3. And then I'm growing further upwards and steeper. And as I'm tracing out values of near my slope field, I'm kind of also tracing out roughly how my function looks like, right? And I hope that intuition kind of gets clear. And you see, oh, I've drawn out like a parabola looking thing. And if we were to analytically kind of find out what the function that leads to this derivative, you know it's like some x squared plus some constant. And that kind of matches up with our intuition over here. Because let's say we had x squared plus some constant is equal to 2, right? And if x of 1, so that you have 1 plus c is equal to 2, and then c is equal to 1. So you get x squared plus 1. And that's roughly what we've drawn out over here. We've drawn out a parabola with a y-intercept at 1, and it looks like this. And we did this all through the slope fields. And I just chose an easy example so we can confirm it analytically, and you can kind of get that intuition of how a slope field, and if we were to trace out the change in how our function will look around the slope field, we'll get the original function back in a more numerical way. And one other thing to notice about this is if I were to change my initial point from y of 1 equals 2 to, let's say, let me change the color to represent another graph, to y of 0 equals 0, now our slope fields will like kind of, well, firstly, this analytically is going to correspond to the graph of x squared. But if we also follow out and trace out our slope fields, we're going to kind of get this other parabola. And we're going to see it's like a shift, right? It's not the original parabola that we get. And this kind of confirms the whole idea of us needing not only the derivative but also an initial value. So IV is initial value plus the derivative to get us a unique graph. Because we just saw over here that depending on our initial value, the original graph can be different. And just having the slope field by itself will not be enough information to give us the original graph back. And even when we do other analytical methods, just having the derivative is not enough. We need the initial value. And I hope looking at the slope field kind of confirms and motivates why that is the case. So that was the idea of slope fields. And I do agree that this example that we did of dy or dx is pretty simple, but I hope the simple example kind of gave intuition of why slope fields are powerful, especially when we cannot do these two things, or when we cannot do these two things, and we're only left with using this more I would say rough method of finding out the original function given an initial value and the derivative. But yeah, that was slope fields and initial value problem.